Tu le mets dans le chat et tu expliqueras au début. Voilà, donc les gens arrivent.
Voilà, c'est fait.
Je ne le vois pas dans le chat.
Recording in progress.
Tu l'as mis dans le chat? Tu l'as mis dans le chat, je ne vois pas.
Oui, oui, je l'ai mis. Je l'ai mis. Alors,
je ne le vois pas. Je ne le vois pas.
Le
chat du Zoom.
Bah, ça a l'air d'être là. Hein. Bon, c'est pas très grave.
C'est le chat du Zoom ou c'est autre chose?
C'est le chat, je pense que c'est le chat du jour, oui. 21 juin. Et
parce que je vois.
Là, j'ai l'impression que mon message a été envoyé.
Ah, il n'est peut-être pas arrivé encore. Mais,
ah, c'est sur la plateforme vidéo.
Ah, c'est sur la plateforme. OK, très bien.
Ah, OK, d'accord. Oui.
Donc, là, tu as un petit chat à côté où les gens posent des questions pendant l'exposé, quelquefois.
Ah, OK, oui.
Moi, je le surveille et dès qu'il y a une question, je t'interromps et je te pose la question.
D'accord. Alors.
OK, on attend encore une petite minute et puis on y va. So, okay, welcome everybody. Welcome back, everybody. So I'm happy to introduce Antoine Song from University of Berkeley. And Antoine will speak about minimal volume, but more than that, essential minimal volume. So Antoine, please, you can start.
Thank you. So thank you for the invitation. I'm really happy to be speaking in Grenoble. So the topic today is going to be, and for my 4 lectures actually, it's going to be the condition that the sectional curvature is bounded from below and from above. And I'm interested in that condition because it's a condition that's very well understood in some sense, and it's clear, it's closely related to topology. So you can really relate the geometry to the topology in a very nice way. And this is what I'm going to try to explain in these lectures. And also this condition, of course, is related to condition on the Ricci curvature. So at least historically, a lot of results say for Ricci curvature were first proved for sectional curvature. So it is worth studying sectional curvature and see what you can prove. That might give you some intuition or inspiration for other kinds of curvatures and other generalizations. And also, so even though this condition is relatively very well understood, there are still quite a lot of open questions that seem very elementary, and curiously, people are not able to answer these questions. And I'm going to state some of these questions and conjectures. All right, so what's the goal of my lectures? First, I want to introduce those invariants that are in the title. Introduce mean-vol, essential mean-vol, and give you some intuition and theorems about these quantities, these invariants. And secondly, I want to talk about collapsing theory. So I could have given as a title for my talks, collapsing theory of Cheeger, Fukaya, Gromov, but I'm going to use minvol and S-minvol as a pretext to present you this collapsing theory, which is due to Cheeger, Fukaya, and Gromov. Let's see. So the plan for my week is going to be like this. Roughly speaking, each section is 1 day. The first section, which is today, I'm going to give some definitions and state some results. In my second section, I'm going to start talking about collapsing theory, because we will see in my first section that when you want to study minimum volume and essential minimum volume, you really need to understand actually what's happening in the collapsed part or in the collapsing part. I'm going to explain what that means. So my second section is going to be the first things that you can say about collapsing theory. And there's something, a basic structure that is called F structures that is due to Cheeger and Gromov. And I'm going to explain what these are. And using F structures, these so-called F structures, you will be able to have some collapsing constructions. So constructions of continuous families having some particular behavior. In my third section, I'm going to continue on collapsing theory, and I'm going to this time talk about N structures. So N structures were due to Cheeger, Fukaya, and Gromov, and N structures generalize F structures, and in some sense, N structures capture entirely what's happening in the thin part of manifold with bounded sectional curvature. So it's a very far-reaching theory, and I'm going to talk about that in my third section. And in the last section, I'm going to give a corresponding collapsing construction. So this time a collapsing construction that corresponds to this N structure. So please. And we'll see some applications. So that's the plan. All right, so I'm going to first give you some quick definitions because minimum volume and essential minimum volume are easy to define. No? Let's see. First, a notation. So in my talk, M is always going to be a closed manifold of dimension N. Of dimension N, and we will denote by this curly M the set of metrics on M such that the sectional curvature of the metric is between -1 and 1. And in some sense, all my lectures are going to be about studying that space, right? So what is the minimum volume? The minimum volume of your manifold is just going to be the infimum of the volume over that space. Over that space. And so it's a geometric way to measure the complexity of your manifold. And it was introduced by Gromov. Who had the idea in the 80s to kind of measure topology by using geometry. All right, so you can also define a variant, a cousin of this invariant, which I'm going to call the essential minimal volume. But first, so let me give you another notation. So for all delta positive, you want to denote by m larger than delta, the delta thick part of m. So the delta thick part is just going to be all the points in M such that the injectivity radius is larger than delta. With respect to the metric G. Then you can define the essential minimal volume as follows. It's going to be the limit as delta goes to 0 of the infimum of a volume, this time the volume of the delta thick part. Again, for metrics with sectional curvature bounded by 1. And as you can see here, so the limit exists when delta goes to 0, simply because this quantity is monotonous when delta is varying in one direction. So clearly, from the definition already, the essential minimal volume is upper bounded by the minimal volume. Oh, let me write it down. And in fact, the difference can be arbitrarily large. Maybe I will have time to talk about this point later in the lectures. But first, okay, this is one definition of the essential mean volume, but I want to write down the definition of the essential mean volume, which is closer to the definition of the standard minimal volume. So I want to rewrite the essential mean volume as an infimum of a volume. So let's do that. So writing it as an infimum of a volume is, at least for me, psychologically more satisfying. So how to do this? Recall that, so last week, I think you saw this term at least twice, which is that by Cheeger, if the sectional curvature is bounded by 1 and the injectivity radius is larger than, say, a delta that is fixed, then you have compactness in the C1 alpha sense. So that means you take any sequence, and with these assumptions and a sequence of points, then in the pointed sense, you have Gromov-Hausdorff convergence, and the limit is a smooth manifold, and actually you can upgrade this convergence to a C1 alpha convergence, meaning that the limit has a C1 alpha metric in particular. And so I'm not going to say more about this result, but I want to use this to see what you can say about the essential mean volume. So before giving you a second definition of the essential mean volume, let me define a weak closure of that space of bounded sectional curvature metrics. So in order to define a weak closure, you will need a notion of weak convergence. And the weak closure is just going to be all the weak limits in this sense of weak convergence. So how do you define this weak convergence? All right. We will say that the sequence converges weakly if so if let's see there exists if for any delta there exists an integer q that might be 0, and there exist corresponding sequences 1, 2, q delta, such that okay, I'm going to switch pages such that first the limit along the sequence of the distance between k I L is infinity for any k and L that are not equal among these numbers. Secondly, you want the delta thick part let's see, maybe to be more precise, you want this pointed sequence to converge to a limit in the pointed Gromov-Hausdorff sense. Gromov-Hausdorff sense to a limit for, let's see. So the limit is a metric space for any k, one of those integers. And for any sequence of points pi inside the delta thick part of gi, the distance of pi to the set of those points, reference points, is going to be bounded. So is bounded as I goes to infinity. Oh, all right, so it's just a technical way, rigorous way to say the following. For any delta, the delta thick part of your manifolds is converging in the multi-pointed Gromov-Hausdorff sets. And if that's the case, you just say that you are weakly converging. So if that's the case, the weak limit of this sequence of metrics is defined as the union over delta of the partial limits. Right, so for, let's say, any delta, this is well defined, and for two deltas, one bigger than the other, one of those limits is included in the other naturally. So you can take the direct limit if you want. In other words, you take just the union as delta goes to 0. Is there any question on that definition? All right, so this is the natural definition of a weak limit, if you want, that enables you to not lose too much information. And so because of this weak limit, this notion of weak limit, you can define the notion of weak closure of your set of metrics with bounded sectional curvature. As all the possible weak limits of metrics in this set of metrics with bounded sectional curvature. And of course, a smooth metric with bounded sectional curvature is going to be its own weak limit. So this closure contains your original set. And now the claim is that the essential minimum volume of M is the infimum of the volume over this larger set. Right. So this is that was our what we wanted to do, which is to rewrite the essential minimum volume as an infimum of the volume. And in order to essentialize the main volume, the idea is just to enlarge a little bit the space of bounded sectional curvature using this notion of weak limit, say. And moreover, so that's part of the claim. Because of
when there is a question on the chat for you.
Yes. So, okay, so the question is about how to define this weak limit. Is it some kind of colimit to do that? Yes, so these spaces are nested. It's a sequence, it's a nested sequence of spaces. One is naturally embedded into the other. So when you take, when you look at this limit, so delta is fixed, you take the limit, that gives you a space that is y delta. So when you take a smaller delta, the corresponding y smaller delta contains this y delta. So this weak limit is the direct limit of these spaces. You take the union and you identify points in a natural way when they're equal according to these embeddings. So let me know if it was not clear enough. So now I'm going to continue. Because of the theorem of Cheeger, okay, so no, it follows from the fact that okay, so it does not exactly follows. Okay, what should I say? So once you know that for any delta, this converges, so you have, let's say you have a sequence of delta going to 0 such that this converges, then it follows that if you take a smaller delta, the limit corresponding to that delta contains the other limits in a natural way. Is it the question? So another question, is the union over K disjoint? Yes, yes, because so in the definition, I'm making it carefully that, so I impose that you take sequences that are really diverging from each other. So the limits are really corresponding to different regions of your manifolds. And so the union here is going to be a disjoint union over K. And the integer Q delta depends on delta. So yeah, right. Anyway, one thing about this is because of Cheeger, so actually the essential mean volume is realized by one of those weak limits. So sorry. So it is the volume of a manifold in this closure, weak closure. And moreover, so automatically, maybe I forgot to say that maybe automatically this is a complete C1 alpha metric. And M infinity is a smooth manifold. So in other words, you can think of essential mean volume simply as the natural variant of the minimal volume, which is actually realized by something, which is realized by a Riemannian manifold in a certain closure of the space of bounded sectional curvature metrics. So that's it for the definitions. Let me move on to some results that I'm going to give you some what I think are the main results for the minimal volume. Some important results. Important results. So all these results that I chose are lower bound for the minimal volume or the essential minimal volume. Some of them are topological, some of them are more geometric. So let me say something. There are very few general, say, topological lower bounds, so obstructions for the minimal volume. Or similarly for the essential minimal volume. There's a trivial bound, a quote unquote trivial bound, which comes from characteristic numbers. Any n and characteristic number p, you have the following. You have that the minimal volume of M is lower bounded by a constant depending on n and your characters number times the characteristic number of M. Characters number, for example, the Euler characteristic. And why is that? Well, that's because by Chern-Weil, you can write this as an integral of a polynomial in the curvature tensor. Curvature tensor. But if you assume that the curvature is bounded by -1 and 1, then this is going to be less than the integral of 1, right? Which is the volume, which is what you want.
Antoine, there is another question on the chat.
Oh, thank you. Oh, yes. The question is about those metrics that realize the essential minimum volume. Exactly. So it can be non-connected, and moreover, in general, you have infinitely many connected components. All you know is that it's a C1 alpha metric and it's complete. But you might have, you start with M, which is connected and nice, but the metric that achieves the essential minimum volume might have a lot of connected components. And it's a theorem that says that the number of components is finite, but it might be non-connected. So the answer to your question is yes, it might be non-connected. If you take a surface of, say, genus 2, you can look at the metrics realizing the essential minimum volume of a surface of genus 2, and you might obtain a number of pair of pens in the limit. So disconnected union of pair of pens that are hyperbolics. So maybe let me write. Many connected components. Right. Okay, let's come back to some lower bounds for the minimal volume and the essential minimum volume. Again, you have this trivial bound by characters numbers for the minimum volume. So for the essential minimum volume, it's kind of a little bit less trivial actually, but you still have a bound, a lower bound by the Euler characteristic. Euler characteristic. And it's less trivial because it really needs this theory of Cheeger and Gromov, but at the end, by the end of, say, the second lecture, so the second day, I think we will understand why the essential minimum volume is lower bounded by the Euler characteristic. But I put that in the category of trivial bound because they're closely related. So that's one bound, and there's exactly one other general topological lower bound that's known for the minimum volume, which is given by the notion of simplicial volume due to Gromov. So for the second lower bound, we need the notion of simplicial volume.
There is one more question on the chat, sorry.
Um, so it's a polynomial. So okay, any characters number, I'm going to use as a definition of characters number for me, any topological invariant that can be written as the integral of a polynomial in the curvature. So at least, for example, you take the other characteristic, the signature in dimension 4, for example. These are examples of what I'm thinking as characteristic numbers. So, for the second lower bound, again, let me come back to what I was saying. You need the notion of simplicial volume. That's usually denoted by that. Let's see. How do we define the essential volume, the simplicial volume? The simplicial volume, contrarily to the middle volume and the essential volume, is a purely topological quantity. It's due to Gromov. And it's a kind of topological minimum volume if you want. It's the infimum of the following sums. Such that you have the following. So you can find simplices sigma 1, sigma L from the standard simplex such that the sum of those simplices with weights Ri is a cycle that represents the fundamental class of M. All right, so this means the fundamental class. So it's, okay, so let's assume that M is oriented. If it's not oriented, you take the double cover. So say if it's not oriented, you just take the double cover, connect the double cover, you get a number. And if you divide by 2, by definition, it's the simplicial volume of your non-orientable manifold. All right, so here, this is the standard simplex. Right. And one thing to pay attention to is that these numbers Ri are really to be taken in the set of real numbers. Otherwise, you don't, if you take Ri to be in Z, say, you don't get such a nice invariant. And in some sense, this simplicial volume measures the minimal amount of simplices that you need in order to cover your manifold. Simplices needed to cover your manifold M. By cycle, I mean that the combinatorial boundary of this guy, which is the sum, the weighted sum of the combinatorial boundaries, is equal to 0. It's important that you're really using this combinatorial boundary. So let's see, is there a question? Yeah, that's right. The simplicial volume of a sphere is, is equal to 0. No, it's not 2, it's 0. So let me, in the next example, I'm going to explain, compute the simplicial volumes of surfaces. Because, maybe the confusion comes from the fact, okay, I see. Here, the simplices are completely wild, right? They're not immersed, they're not embedded, they cover themselves, they're just continuously mapped. And moreover, these Ri, again, are real numbers, right? And so that's why I'm going to explain why the simplicial volume of, say, a sphere is 0. Let's do that. Yeah, it's a bit of a strange definition the first time you see it, but let's look at some easy properties of the essential mean volume. And after these properties and these examples, I'm going to state the theorem, the lower law. Properties. The easy property is that if you have a non-zero degree map, say degree D, map from one manifold to the other, then you have the following inequality, meaning that the simplicial volume of your domain manifold is at least D times the simplicial volume of the target. And in order to see that, you look at the definition. Indeed, if you have a sum of simplices that represents M1, the fundamental class of M1 in its nth homology. This sum of simplices is sent via the map, okay, I'm going to call this continuous map F, via F to another sum of simplices, right? And because F is of degree D, automatically this sum of simplices is representing D times the fundamental class of M2. What it means is that 1 over D of this sum represents M2, and then that means that you have what you want because the simplicial volume of M2 is going to be smaller than 1 over D times the sum of the Ri. And you can take it as close as you want to the simplicial volume of M1, right? M1. So that's the property that follows from the definition. It's almost by design that you want a quantity that behaves like this. And once you have that, you can actually already compute the simplicial volume of any surface. So let's see. How do you do that? As a consequence, if sigma gamma is let's see, is surface of genus gamma, then you have the following. The simplicial volume of sigma gamma is going to be 0 if the genus is 0 or is equal to 1, and it's equal to 4g minus 4, so which is equal to 2 times the Euler characteristic if the genus is larger than 1. So why is that? For the sphere and the torus, that follows almost directly from the easy property, and that answers the previous question. Because these manifolds have self-maps of non-zero degree. Apply the easy property, get that the simplicial volume is 0. It cannot be a positive number just because this positive number needs to be equal. This number needs to be equal to a positive multiple of itself, right? And so that's fine for spheres and tori. What about higher genus? First, you check that the simplicial volume of a surface of the genus gamma is always less than 2 times the Euler characteristic plus 4. So why is that? You just need to find an explicit triangulation with that many triangles, right? This is the goal. And in order to do that, well, you just look at the fundamental domain of your surface of genus G. Let's see, let me try to, okay. So, what I'm trying to represent here is a polygon that represents a fundamental domain of sigma G. And with the identification that are given on the sides, right? So here, for example, is genus 2. What you do is you take the trivial triangulation that you can imagine for this surface from that polygon. And you can count the number of triangles here. It's exactly this number. I think. Then, okay, so that's, let's see. Right, but that's not optimal. However, you look at this now. You look at the degree D cover of your surface by high genus surface. Then by the easy property again, you have that you have this inequality, but we just saw that the simplicial volume of this larger genus, this covering space, is less than 2 times the order characteristic.
There is a question again.
That's for yes, thank you. And yes. So the genus here is gamma. G is for the metric. Sorry for the typo. Let's see. Let me come back to this covering surface. So the covering surface has simplicial volume at most 2 times the order characteristic plus 4. This is what we saw in the first step. But because it's a decover of the original surface, so you can write this following equality. Now you can just send d to infinity and you get an optimal upper bound. So that's for the upper bound. And it remains to show that it is an optimal upper bound. So you want to show the lower bound, that it's also a lower bound. Good. Next. So how should you do that? Well, what you want to show is this. And in order to show that, you can check the following. So given cycle that represents your surface, you can look at the volume. You can first put the hyperbolic metric on the surface. So this is a geometric step that is very useful in this proof. So once you put this hyperbolic metric on sigma gamma, you can talk about the volume of the simplex simplices. Okay, so so first. We can make these simplices straight. So at the beginning, a simplex sigma might be quite messy, etc. But what I'm claiming is that once you have this hyperbolic metric and you have this, say, a given simplex, you can straighten it so that now you have very nice simplices. Where this is a geodesic that is homotopic to the corresponding side. And what you can say then is that 2 pi times the Euler characteristic of your surface is equal to the sum of the volumes, because it covers it covers the surface with algebraic multiplicity 1. But this is less than pi. So you can check that in a hyperbolic surface, any simplex that has geodesic sides is going to have absolute upper bound on the volume. The volume of sigma I is always upper bounded by pi. Once you realize that, then these lines give you what you want, the lower bound for the simplicial volume, and you're done. Singular simplicial volume. Let's see how. Yeah, I'm not sure of how to answer that question. One remark is that the straightening thing only works, actually, at least it works under some assumptions. For example, here you need some negative curvature. Once you have negative curvature, this method of straightening a simplex is well defined. But in general, for a general metric on a general manifold, you don't have a well-defined way to straighten a simplex. But yeah, it's a good remark. It's at least in spirit, clearly it's similar. You simplify the simplices that you have in order to be able to do computations. So that's it for the simplicial volume of surfaces. And now that you have a good feeling of what the simplicial volume is, let's state the theorem of Gromov. Does this volume always turn out to be an integer? No. So the values of the simplicial volume can be non-integers. They can be non-rational. In dimension 2, as you can see, it's always a nice integer. In dimension 3 already, it is not. But in dimension 3, the set of possible simplicial volumes of closed three manifolds coincide with, essentially coincide with the volumes of hyperbolic three manifolds. And in any higher dimension, so in any dimension at least 4, the simplicial volumes of closed manifold is dense in the real line. Let's see. Okay, so finally, the theorem of Gromov, which again, surprisingly, is the only general topological lower bound for the minimal volume. A metric with bounded sectional curvature. Then the volume of the deltathic part is lower bounded. Sorry, is lower bounded by the simplicial volume. So the meaning of that result is that you have this geometric quantity, the volume, and it's lower bounded by this purely topological quantity, which is the simplicial volume. And in particular, as a corollary, you get that both the minimal volume and the essential minimal volume are lower bounded by the simplicial volume. Okay, first by definition, that's first bound, and the second bound comes from this theorem. Let's see, I still have 30 minutes. I'm hesitating whether or not I should give an outline of this theorem. So maybe not, maybe, okay, so for those who are interested in outline, maybe you can ask me later, but maybe I will have no time today because I want to move on. But so that's it for the topological lower bounds. As you can see, it's not much, but there are not many results. Here's a geometric lower bound. It's an important result. It is due to Lisson-Courtois and Gallo. That says the following. Actually, the minimum volume, okay, it's a rough invariant because it's defined using the sectional curvature, but quite amazingly, you can compute it for hyperbolic manifolds. That's the content of their theorem. Then the minimum volume. The minimum volume of X is, well, the hyperbolic volume. Meaning that, okay, you take any other metric on X with the bounded sectional curvature by 1, then you will have actually at least as much volume as the hyperbolic one. And a remark here is that by the end of lectures, I hope to explain why this is also true, in fact, with the essential minimum volume. So we'll see. It also holds for the essential minimal volume, meaning that the essential minimum volume of the hyperbolic manifold is also the hyperbolic volume. In dimension 2, S min vol equals min vol. Oh yeah, that's a good question. So in low dimension, S min vol and min vol, there's no difference. I didn't compute the minimum volume of surfaces. I leave it as an exercise. I forgot to do this, but let me write it as a remark. Dimension 2, 3. Volume is equal to the minimum volume. So in low dimension, there's really no distinction between the two. And in dimension 2 is just a direct computation, while in dimension 3 already, to prove this, you need some theory. It's not completely trivial that this is true. But it comes from the fact that in dimension 3, if you look at the thin part of a manifold with bounded sectional curvature, you can always collapse this thin part with a bound on the sectional curvature and volume going to 0. That is always possible. That is not always possible in higher dimensions. Okay, I'm continuing with my remarks. The minimum volume and the essential minimum volumes are quantities that are defined using the smooth structures. And in fact, they depend on the smooth structures. So that was a result of Laurent Bessières and also later in dimension 4 by Kochik, min vol, and also S min vol depends on the smooth structure. Of and meaning that in high dimensions, you can find two homeomorphic closed manifolds that are smooth and non-diffeomorphic, and they have different minimal volumes. Right. And next, to kind of illustrate our ignorance about minimal volume and the essential minimal volume, let me give you two conjectures. The first one is an old one, which is due to Gromov. And simply it says the following. They should exist a dimensional constant such that if the minimal volume is less than this constant, then it's actually vanishing. To 0. So you have something that is known about that. So this is known in dimension up to 4. So in dimension 2, it's trivial. In dimension 3, it's not difficult. In dimension 4, it is difficult, and it's due to wrong. We will also see that my Cheeger-Gromov, the gap conjecture is true for the essential minimal volume. And here there's nothing to prove once you know the work of Cheeger-Gromov. It is a corollary of the work of Cheeger-Gromov that this gap conjecture is true for the essential minimal volume. Whenever the essential minimal volume is small enough, then actually you're 0. So from this point of view and the previous results, you see that the essential minimal volume is a kind of idealized version of the minimal volume. It satisfies a lot of properties that you want it to be satisfied by the minimal volume. But here's another conjecture that also is open for the essential minimal volume, which is you want to find other topological lower bounds for the minimal volume and the essential minimal volume. It's a bit scandalous that there's only 2 available, right? So let's try, at least in dimension 4, what you can propose is the following. You take any smooth closed 4 manifold, take any genus that is larger than 1, then you would like to say that the minimal volume of the connected sum of these 2 guys, so n and the product of the 2 sphere with the surface of genus gamma, this is larger than the constant times gamma, the genus of the surface. So you can try to imagine similar conjectures in higher dimension, but let's just focus on dimension 4 since it's the first non-trivial dimension. So that would be nice. That would give a third topological lower bound for the minimal volume. That is kind of general. All right, so let me conclude this first section, and I want to move on to the second section. So in some sense, studying these kind of invariants, min-vol, S-min-vol, that's really about studying possible closures not only the one that I defined, but other kind of closures of the set of metrics on the sectional curvature. And in turn, that requires the understanding of the thin part. And the thin part is going to be the object of my talks, the topic of my talks for the next 3 days, basically. The thin part being the part where the injectivity radius is small. And that's going to be given by the Fukaya Gromov theory. Let's see. Let's see. All right, so let me move on to the second part. Which is about the first structures that you can find when you try to study collapsing theory, and it's called F structures. And I'm going to give you a corresponding collapsing construction. All right. So when I say that GI, a sequence of metric collapses, what I mean is simply that the sectional curvature is uniformly upper bounded, so independently of I, and the injectivity radius goes to 0. Everywhere. Note that I'm not requiring that the volume is going to 0. That's a different condition. I'm just assuming geometric collapsing, which means that locally the volume is going to 0. But maybe the global volume is still big or whatever. We do not care. We just impose these conditions on the injectivity radius. Also, a remark, maybe you saw that last week, which is when the sectional curvature is bounded between -1 and 1, small injectivity radius is equivalent to saying that the volume of the one ball is small. I have a quantitative version of that statement. Before giving you something about the general theory, I should give you some basic examples of collapsing. And these examples are going to be based on the following principle, which I'm going to call rescaling along Killing fields. Let's see. You look at the metric, any metric on M, and you're given a Killing field. It generates by integration an OR action, right? And the idea is to rescale your metric in the direction that are tangential to the Killing field. You want to make it smaller and smaller, and you want to check that the metrics that you're obtaining have bounded sectional curvature, and moreover, the injectivity radius is going to 0 if M is closed. So M is compact here. You decompose your metric into two parts, the tangential part and the orthogonal part. and you define the collapsing family to be G delta, you rescale by delta, the tangential part. And I'm going to explain to you why this is really a collapsing family of metrics. Right, so let me write down the claim. Delta goes to 0, sectional curvature is upper bounded by a constant that might depend on the original metric, but at least it's independent of delta. And the injectivity radius goes to 0 everywhere. In other words, you have collapsing. Yes, so let's prove that. Let's look at a point in M. And let's look at the R fiber that goes through P. That's the R fiber. And then locally, just near P, everything is going to be in a small, very small neighborhood of P, where everything is nice. You can find a transversal to the R fiber that I'm going to call omega. So what do I mean by transversal? So at P. It's a dimension 1 submanifold that is embedded going through P and transversal to all the R fibers that it needs. To the R fibers. All right, and the proof is then going to be just a computation in charts. It's something that is simple, but one should do it once in their lives. So let's do that. Let y be coordinates on gamma, so that P is going to be the 0, 0, 0 point, and let x be the R coordinates. That corresponds to the R action, in other words, to the killing field. Okay, so x equals 0, and you want x to be equal to 0 on your transversal omega. Then what you can do is to extend the y coordinates to the whole neighborhood. Right now you have the y coordinates on omega, and you extend it in a natural way to the whole neighborhood. Simply by projecting on the transversal. Along the fibers. In these coordinates, switching to these coordinates, the X vector field is parallel to the R fiber, and you can look at the y derivative, and you can decompose it into two vectors, and the sum of two vectors, again, one which is tangential to k, and this is orthogonal to k at any point. So the y direction might not be perpendicular to our fiber, so you decompose it into a perpendicular part and a parallel part. And now you have all the notation required. You can write down your original metric as such a matrix in the coordinates, of course. I'm just going to write down what this matrix is. Let's see. And B and L, P and the L. So this is something you can check. Right, so A is a 1-1 matrix, B is a n-1 matrix, and C and D are square matrices. Anyway, in these coordinates, P delta is then going to be equal to, basically you multiply everything by delta square except the orthogonal direction, right? Because we're only rescaling along the killing fields. And then here it's not clear that this metric is still going to be non-degenerate in the limit, but we can just change coordinates to see that actually this metric is a nice one, converging to a smooth one. Change coordinates. So when you change coordinate, you rewrite what your metric is in this coordinate system, then you get something else. You get, now in this new system of coordinates, you see that this metric is converging smoothly and nicely to A0, A0, 0, and D. I want to change page, so here. A0, 0, D, and remember A, B, C, D only depend on the y coordinates. Y coordinates. Because K is killing. Because you're moving everything by isometry because of the definition of the coordinates. And so that means that this convergence here is really a smooth one. So once you know that the metric in some coordinate is converging smoothly, then clearly the sectional curvature is going to be bounded, right? And moreover, let me write it down.
Antoine, we lost the connection. Okay, it's back. Your microphone is shut.
Okay, you can see that, right?
Yeah, very good. Okay. Very good.
So because the metric, we just saw that the metric written in a new coordinate system is actually converging to something smoothly. So the sectional curvature along that family is bounded because the curvature is just the second derivative of your metric somehow. And the injectivity radius is going to 0. You can check that because compactness of the orbits. Remember, M is compact. M is compact. So that is the classical example of collapsing when you just rescale along Killing fields. And this you can check as if you want an exercise that this generalizes to when you have multiple Killing fields and they commute. It's important that the Killing fields commute. So I'll write this remark, this trick. Case where we have many Killing fields, a finite number of Killing fields, which are commuting. In other words, you have an R to the power L action. And it's a general case of a torus action. I'm going to end today with an example that is going to be important for us. That is an application of this trick. Look at the flat interval cross R2. So you're just looking at 0, 1 with the usual metric times the flat R2. So I'm going to denote this flat metric by H, and let's B theta be the rotation of R2 with angle theta. And I'm going to glue the two boundaries of your first manifold using this rotation, okay? So there. So you glue one boundary to the other by using your rotation. So you identify each point with its image by this rotation of angle theta. From a smooth point of view, you don't get anything weird. You just get an S1 cross cross R2, right? So diffeomorphically, it's diffeomorphic to S1 cross R2. However, what's interesting here is that you have this metric, this flat metric, and the behavior of this flat metric is going to be interesting. So apply the rescaling trick, that example, to okay, I'm going to denote it by that. I don't know if it's a good notation. What it just means is that the rotation naturally gives you a Killing field. So you rotate, and in the same time, you go up. So this is the rotation, this is going up. So that means we have the following Killing fields, right? So at time 1, when you integrate that killing field at time 1, you rotate it by angle theta, and also you got up by 1. Okay. So you have a few cases that I want to explain. Okay, don't have time, so I'm just going to continue next time. But let me say first that if theta is 0, then as delta goes to 0 and you rescale it, you get a GH limit, then rescale. You get a Gromov-Hausdorff limit, which is the flat R2. And next time I'm going to explain to you, finish this example and continue with F structures. And the goal is to see that by Cheeger and Gromov, this and generalization of this trick are essentially the only way to collapse manifolds with bounded sectional curvature. So it's really nice. For next time, I'm going to explain what the GH limits are when theta is either rational or irrational. And you can maybe think about that a little bit. So thank you for your attention.
Thank you, Antoine. So there is still a question in the chat, and maybe there will be more questions.
Let's see. Trying to see them. Okay, the fact that the collapsing metric is converging thanks to is confusing, since it seems that at the limit, the dimension of the space gets lower. Yes, so what we did is, in fact, we are looking at small neighborhoods of P where you can write down these coordinates, and this neighborhood is getting smaller and smaller as I goes to infinity. But it doesn't matter, because what you're interested in is just the behavior of the metric in a very small neighborhood. You just want to know the second derivative of this thing. So even though this neighborhood where you can write down these nice coordinates is getting smaller and smaller, you can imagine that it's part of a bigger manifold that for example, if you look at the universal cover, then there you can write down the same metric. And here, the neighborhood, you can take it of the uniform size.
Okay, are there more questions? No? Okay, so if this is not the case, thank you very much, Antoine, and we'll meet again tomorrow. And we stay in Berkeley, actually, for the next section. Merci beaucoup, Antoine. À demain.
Merci.
J'arrête l'enregistrement. On fait pour la. Ah oui, l'enregistrement, c'est bon.